of the equilibrium constant of the backward reaction. That means that Kf will be equal to 1 by Kb. It is inverse of each other. The rate of the reaction will be directly proportional to the concentration of the reactants, right? And it is proportional to the concentration of the reactants raised to the power which is equal to the stoichiometric coefficient. Rate of forward reaction and rate of backward reaction will become equal. So what does that mean? Rf will be equal to Rb. Rate of forward reaction will become equal to rate of backward reaction. Hello everyone, this is Ambli Unnikrishnan from the Department of Chemistry. So today we are back with session 2 of the chapter Equilibrium. So in the last session we introduced what is equilibrium, right? We understood what is equilibrium and the classification of equilibria, and then physical equilibrium in detail we studied in last session, right? So physical equilibrium involves physical processes, right? Yes, and equilibria in physical processes, equilibria involving dissolution of solids or gases in liquids, right? Yes, as well as the general characteristics of physical equilibrium. So physical equilibrium, that is the first classification we have completed in the last session itself. So in today's session, as discussed in the previous session, we will be studying about the equilibria of chemical reactions, right? Equilibrium in chemical processes and characteristics of chemical equilibria also, as well as the types of chemical equilibrium and law of mass action, which is a very important law of mass action or law of equilibria. Even this we will be studying in this session. Okay, so in the last session also we have studied this, what is a reversible reaction and what is an irreversible reaction. So in equilibria, the equilibrium is attained only if it is a reversible reaction. That means it has to happen in the forward reaction as well as in the backward reaction. It should happen simultaneously and in the equal rate as well, right? So let's see reactions in which reactants react to form the products under certain condition, and the products also react to form reactants under the same conditions are called as reversible reaction. That means reactants should combine and form the product as well as the products should combine. Now, in the reverse reaction, what happens? The products will act as the reactants, right? So, that is what is written here. The products will also combine and form the reactants. Both way the reaction should proceed, right? So, for example, calcium carbonate decomposes to calcium oxide and carbon dioxide under certain temperature and pressure conditions. At the same temperature and pressure conditions, calcium oxide and carbon dioxide will combine and form calcium carbonate. So it is a reversible reaction. So it is very important that this reaction should take place in the same condition itself. Okay, so if the temperature and pressure conditions changes, the equilibria also affects, right? The next one is nitrogen and hydrogen combines to form ammonia, and at the same time ammonia can go back to nitrogen and hydrogen. Okay, now the reactions in which only reactants combine to give products but products do not react to give back the reactants under the same conditions are called as irreversible reaction. That means magnesium and oxygen combines to form magnesium oxide, but magnesium oxide does not give back magnesium and oxygen. So this is only a one-way reaction, right? So that is why it is called as an irreversible reaction. I hope it is clear. Now we are going to consider, that is, we are going to study about what? Chemical equilibria, right? That is involving chemical processes. So we are going to consider a reversible reaction. A plus B is combining to form C plus D, as well as C and D is combining to form A plus B, is conducted in a closed vessel at constant temperature. In the beginning, velocity of the forward reaction is maximum and the velocity of the backward reaction is 0. That means that A and B are combining to form C and D in the beginning, and C and D will also start combining and form A and B, right? So initially in the beginning only A and B is available, right? These are the reactants, only A and B is available. So what happens? The rate of the forward reaction will be more. The speed with which or the velocity with which the forward reaction, which is forward reaction A and B combining to form C and D, this way. So the forward reaction or the velocity at which the forward reaction is taking place will be more, right? Initially there is no C and D, Right. Now, once C and D is also starting to form, now what happens? Yes, this side also the rate increases. Now that means the backward reaction velocity also increases. And at a point, what happens is the velocity of the forward reaction and the velocity of the backward reaction will become equal. Right. So let's see, as the reaction proceeds, velocity of forward reaction goes on decreasing. Why it goes on decreasing? Yes, because A and B is getting used up, right? A and B is combining and forming C and D, right? Yes, and velocity of backward reaction goes on increasing after some time. Velocity of forward reaction will be equal to the velocity of that of backward reaction. V1 will be equal to V2. So the velocity after some time, what happens to the velocity of forward reaction and backward reaction? It will become equal. That is, it is at a state of chemical equilibria now. So it was a chemical process, right? So what happens? Initially, the forward reaction velocity was more. Then what happens? After a while, it starts decreasing and the backward reaction velocity increases. And after a certain point, what happens? This will become equal, right? Now we can say that the system is in chemical equilibrium. So let's understand it with the graph. So it's a concentration time graph. So as you can see, initially the concentration of the reactants will be more, right? There will be no concentration of the products here, that is C and D. That is why it is in 0. So initially the concentration of A and B is shown here. Now what happens? As time proceeds, the concentration of A and B will decrease, right? A and B will decrease. Now what happens to the concentration of C and D? It is being formed, right? So concentration of C and D will increase. Now you can see here the concentration of products is increasing, the concentration of reactants is increasing, right? And at a point or after that point, what happens? Yes, the concentration becomes equal. That is why you can see a straight line here. Even though the time is proceeding and the reaction is taking place, there is no effect of concentration with time, right? That is why you can see a straight line here. Is it decreasing or increasing? No, right? After this point, it is a straight line you can see. That means that concentration is not depending, right? So this state is called as the equilibrium. I hope it is clear. Now, let's understand the characteristics of chemical equilibria. Now, chemical equilibria is dynamic. Dynamic means what? As you can see here also, when you observe the graph, you might feel that, okay, now it has become a straight line. That doesn't mean that. You might think that, okay, the reaction has stopped happening. That means now A and B is not reacting as well as C and D is not formed also. You might think like that. But it is a dynamic equilibrium. That means that it doesn't stop. It's not static equilibrium. The reaction will be still taking place. But the opposing reactions, that's the forward reaction as well as the backward reaction, will be taking place in equal rate and simultaneously. So we feel that the reaction is not taking place. That is why it is dynamic. The reaction will be continuing. So it is very important to understand, once the system is attaining equilibrium, it doesn't mean that the reaction stops. Right? The reaction will be continuing, but it will be in the same rate. Right? Now at equilibrium, the concentration does not change with time. Even that we have observed in this graph. Once the equilibrium is attained, now there is no change in concentration with time. Even if the time goes on, what happens? It is still a straight line that you can observe. It does not have an effect on the concentration. Now, catalyst has no effect on the position of equilibrium. Okay, because it alters both forward and backward reaction to the same extent, but equilibrium attains quickly. Okay, so what is the use of a catalyst? Catalyst is used to generally to speed up a reaction, right? So it is important to know that it does not change the position of the equilibrium. It just helps in attaining the equilibrium much more quickly. Right, because it affects the rate of forward reaction as well as the backward reaction. So it will affect equally. The catalyst will have an effect equally on the forward as well as backward reaction. So the position where the equilibrium is attained won't change, but the equilibrium will be attained quickly. That's it. Right. Now, the position of chemical equilibrium can be disturbed by varying pressure, temperature and concentration. So, as discussed before, the equilibrium, we have to define it under a constant temperature and pressure condition. If we vary the temperature and pressure, of course, the point of equilibrium will also change. Right. It is independent of the initial concentration of reactants and products, but it depends on temperature. So, what does equilibrium depend on? It depends on temperature and pressure, but it does not depend depend upon the initial concentration. So initially how much of reactants or products is available, that does not depend the equilibrium. Only the temperature conditions will affect equilibrium, right? Equilibrium constant. Now, what is equilibrium constant? We are going to discuss in the upcoming slides. Equilibrium constant for a reversible reaction is inverse of the equilibrium constant of the forward reaction. That means that, let us consider the same reaction we have considered before. This is a reversible reaction, right? So, the equilibrium constant for the forward reaction, let us write it as Kf. K stands for equilibrium constant and F is for the forward reaction. Now, for the backward reaction, let us consider it as Kb. Now, what does this sentence say? That equilibrium constant for the forward reaction will be inverse of the equilibrium constant of the backward reaction. That means that Kf will be equal to 1 by Kb. It is inverse of each other. Okay, if you know the value of the equilibrium constant for the forward reaction, the inverse of it, that is 1 by of that, will be the value of the backward reaction, right? Now, if the equation is multiplied or divided, equilibrium constant is equal to its respective power or respective roots. That means that, let us assume that, okay, the forward reaction only I am going to consider A plus B giving C plus D. So now what I am going to do, the whole reaction I am going to multiply by 2. Okay, if I am going to multiply this reaction by 2, initially the equilibrium constant was 2. Okay, so now of course if I am multiplying the equation by 2, that means that the equilibrium constant will also change, right? But how does it change now? What will be the new equilibrium constant? It is not 2kf, it is kf to the power 2. It will become kf square, right? So it will be the power of that value. Whatever value we are multiplying, that will come in the power. So I hope it is clear. So once we do the numericals, it will be clear for you. So now moving on, chemical equilibria, it is classified into two types, homogeneous equilibria as well as heterogeneous equilibria. So from the name itself, you can identify something, right? Homogeneous, something is same there. Okay, so let's see. Equilibria is said to be homogeneous if reactants and products are in the same phase. If they are in the same phase, we call it as homogeneous equilibrium. Same phase means either the reactants and the products, all of them must be in the solid state, or else all of them must be in the gaseous phase, or else all of them must be in the liquid state. It is necessary both reactants as well as products should be in the same phase. Then we call it as homogeneous equilibria. So for example, hydrogen and iodine combines to form hydrogen iodide. Yes, you can observe here it is in gaseous phase. This is also in gaseous phase. This is also in gaseous phase. So this is what is called as homogeneous equilibria. Another example, nitrogen and hydrogen combining to form ammonia. All of them are in gaseous phase. So these are called as homogeneous equilibria. Next one is heterogeneous equilibrium. Equilibrium is said to be heterogeneous if reactants and products are in different phases. That means either the reactant and product will be in different phases. All of them will not be in the same phase. For example, calcium carbonate gives calcium oxide and carbon dioxide. It's a chemical equilibrium. As you can see here, this is in the solid state. Even calcium oxide is in solid state, but carbon dioxide is in the gaseous state. So one phase is different. So it is a heterogeneous equilibria, right? So I hope it is clear. So this is homogeneous and heterogeneous equilibria, which is two type of chemical equilibrium. Now, let us study the one important law of this chapter, that is law of mass action or law of equilibria. Okay, so it states that the rate of the reaction, rate means it is speed itself, that is in chemistry terms we use the word rate. Okay, the rate of a reaction is directly proportional to the product of active masses of the reactants at constant temperature. Okay, so the rate of the reaction or the speed with which the reaction will take place will be directly proportional to the concentration of the reactants we are taking. Okay, so the rate will increase if the concentration we are taking of the reactants will also increase, right? So let's understand and derive the equilibrium constant expression. So it is written as Kc. Okay, K stands for the constant and C. Okay, it is depending on concentration, right? So this is called as equilibrium constant, right? So let's see. We are going to consider a reversible reaction. AA plus BB is giving CC plus DT. It's a reversible reaction, right? That is why we are using this arrow. So now the small letter A, small letter B, small c, small d, it stands for the number of moles, right? And capital A, capital B, capital C, capital D stands for the reactants and products. A and B are reactants, C and D are products. Is conducted in a closed vessel at constant temperature. Now, A, B, C and D be the molar concentration of reactants. So, A is the reactant, right? If I am mentioning it in square bracket, that means that it is the concentration of A, right? So, square bracket will represent the concentration. So, it will be the molar concentration and product A, B, C, D respectively, and let RF and R be the velocity of forward and backward reaction. So, RF will be the rate of forward reaction and RB will be the rate of backward reaction. F and B stands for forward and backward, right? So, according to the law, what does law of mass action say? The rate of the reaction will be directly proportional to the concentration of the reactants, right? And it is proportional to the concentration of the reactants raised to the power which is equal to the stoichiometric coefficient. So, what does that mean? Let us say. So, the rate of the forward reaction, okay, according to the law, the rate is directly proportional to concentration of the reactants. Now, just we are considering the forward reaction means only this part, that is AA plus BB giving CC plus DD. Only we are considering the forward reaction. So, in the forward reaction, which is the reactants? It is A and B, right? So, according to law of mass action, the rate of forward reaction must be directly proportional to the concentration of the reactants, right? So, that is why we are not considering C and D. It is directly proportional to the concentration of reactants raised to the power which is equal to the stoichiometric coefficient of the reactants. That means A raised to the power A and B raised to the power B. So, this stoichiometric coefficient that you can see, that should be put in the power, right? Now, if that is for the rate of forward reaction, how can we mention the backward reaction? So, in case of backward reaction, now it will be CC plus DD giving AA plus BB, right? It is in the backward direction. So, now who is the reactants here, or which are the reactants here? It is C and D. So, how do I write the rate for backward reaction? It is directly proportional to concentration of C and D, right? Now, those are the reaction raised to the power C, raised to the power D. Okay, so that is what is written here. I hope it is clear. Now, where Kf is the velocity constant for forward reaction. So, now applying the law of mass action to the backward reaction, we get this equation. RB directly proportional to C raised to C into D raised to D. So, one more point, what happens is RF is directly proportional to A to the power A and B to the power B. So, to remove the proportionality, we can introduce a constant there, right? So, that constant is Kf. Okay, so you will get it is equal to instead of directly proportional. So, this Kf is the equilibrium constant for the forward reaction. Now, same law of mass action we are applying for the backward reaction. RB will be directly proportional to C to the power C into D to the power D. Now, again proportionality, to remove it, we introduce the constant Kb, where Kb is the velocity constant for backward reaction. Now, we got two reactions, that is RF is equal to Kf into A raised to A into B raised to B. RB is equal to Kb into C raised to C into D raised to D. Now, at equilibrium, what do we know? We already discussed this. At equilibrium, what happens? Rate of forward reaction and rate of backward reaction will become equal. So, what does that mean? RF will be equal to RB. Rate of forward reaction will become equal to rate of backward reaction. So, Kf into A to the power A into B to the power B will be equal to Kb into C to the power C into D to the power D. Right? We already derived what is RF and RB values. Right? We are just putting it in the equation, that is Kf into A to the power A into B to the power B will be equal to Kb into C to the power C into D to the power D. Now, what are we going to do is we are going to just rearrange this equation. So, I am bringing the Kb to this side. So, what happens? It becomes Kf by Kb, which will be equal to, now this term will remain here, this A and B terms I am going to take it to the other side of the equation. So, what happens? It will come in the denominator. So, the equation becomes C to the power C into D to the power D divided by A to the power A into B to the power B. I hope it is clear. Now, what is Kf by Kb? Kf by Kb is equal to Kc, which is the equilibrium constant. Okay. So, from that, what can you understand? See, Kc is equal to. So, what does that mean? Kc, equilibrium constant, is equal to velocity constant for the forward reaction divided by that of the backward reaction, which is equal to the molar concentration of the products raised to their powers. That's a stoichiometry raised to their powers divided by. So what does that mean? Equilibrium constant is equal to Kf, that is for forward reaction, divided by Kv, which is equal to molar concentration of the products, right? Molar concentration of the products raised to the powers, which is equal to their stoichiometric coefficients, divided by molar concentration of the reactants raised to the power of their stoichiometric coefficients. And Kc is called as the equilibrium constant expressed in terms of molar concentration. So, how can you define equilibrium constant then? It is the ratio of velocity constant of a forward reaction to the velocity constant of a backward reaction. In that way, we can write that is Kc equal to Kf by Kb, right? Kf by Kb will be equal to Kc. Another way, it is the ratio of product of molar concentration of product to product of molar concentration of reactants raised to power of respective number of moles. Okay. So, the number of moles were small letter A, B, C and D, right? Okay. So, it is either defined as the product of the molar concentration of products divided by product of molar concentration of the reactants raised to the power which is equal to their number of moles, or else it is equal to the ratio of the velocity constant of forward reaction divided by backward reaction. So, I hope what is equilibrium constant is clear for you and how to derive it, right? So, now let's write down the equilibrium constant for these reactions. Now, nitrogen plus hydrogen, 3 moles of hydrogen gives 2 moles of ammonia. So, how do we write the equilibrium constant? We have already studied this. Molar concentration of the products should be written in the numerator. So, what is the product here? It is ammonia. So, we put it in the bracket and write to represent the concentration, right? So, concentration of ammonia. Now, what do we do with this 2? That is the number of moles that should be present as the power of it, right? So, raised to the power 2 divided by nitrogen into hydrogen, right? Molar concentration of nitrogen into hydrogen, those are the reactants. So, there is no number of moles written here, that means it is 1. So, we just write it as it is. Now, hydrogen raised to the power 3 will come, right? Now, in this case, PCl5 gives PCl3 and Cl2. In this case, you can see that the number of moles in all these cases is 1. So, now how do we write the equilibrium constant? It will be the molar concentration of PCl3 into Cl2 divided by molar concentration of PCl5, right? First, we write the product of molar concentration of products divided by reactants. So, PCl3, Cl2 and in the denominator will come PCl5. Now, next one, hydrogen plus iodine gives 2 moles of hydrogen iodide. H2 plus I2 gives 2 Hi. So, in this case, how do we write Kc? It is molar concentration of the product, Hi. Now, what is the number of moles? It is 2. That will come in the power. Divided by, is there any number of moles written here? No. So, it is 1, right? So, it is just H2 into I2. So, this is how you represent the equilibrium constant. So, in the next session, we are going to study derivation of Kp. Now, what is Kp? We are going to discuss in the next session for gaseous reversible homogeneous reaction. So, what is Kp? We are going to study in the next session. So, Kc, we have already studied that is equilibrium constant. In terms of concentration, we were studying, right? Now, in terms of pressure, we are going to discuss in the next session. So, I hope the concepts that we have covered in the session is clear for you. So, that's all for today. Thank you.